In high-stakes engineering, equations are not unconditional truths. They are tightly bounded frameworks. Step outside those bounds, and edge cases immediately trigger physical failures. One of the most rigid of these boundaries hides inside the standard arctangent addition identity. On paper, this identity neatly compresses two independent angular sweeps into a single equivalent mathematical operation. The operational constraint lives right here in the denominator. If the product of the two inputs, x and y, equals exactly 1, that denominator collapses to 0. This division by zero singularity dictates physical system design across aerospace, electronics, and digital guidance architectures. Mapping exact routes around this specific mathematical void is the essential blueprint for building stable radar networks, RF hardware, and flight guidance code. Inverse trigonometric operations require strict limits called principal value branches. These maintain an exact one-to-one mapping between the input ratio and the output angle, preventing spatial ambiguity. This chart plots a spatial vector against the identity's constraints. Under nominal conditions, where the product of x and y is less than 1, the system behaves. The combined angle stays safely within standard tracking limits, without triggering any mathematical discontinuity. If both inputs are positive and their product exceeds 1, the raw identity fails. The system must execute a positive overflow correction, adding pi to wrap the vector forward into quadrant 2. If both inputs are negative and exceed that same threshold, a negative overflow occurs. We subtract pi, wrapping the vector backward into quadrant 3 to maintain true positioning. Right on the absolute boundary line, where x times y equals exactly 1, the denominator hits 0. The system hits an asymptotic wall, snapping to exactly 90 degrees. Failing to implement these piecewise quadrant correction rules guarantees complete systemic misalignment when crossing that boundary. These phase wraps are mandatory operational guardrails that keep physical geometry tethered to mathematical reality. Taking this mathematical theory into the physical airspace requires looking closely at how our tracking systems calculate absolute convergence angles. This diagram outlines a standard tracking scenario: two independent ground telemetry stations measuring distinct elevation angles, alpha and beta, to follow a single fixed altitude airframe. To lock onto the target, the avionics computer calculates the absolute convergence angle between these two active radar beams. Processing alpha and beta as two separate floating point inverse tangent calculations introduces compounding rounding errors at every step. Instead of calculating them separately, the computer merges the data streams into the identity's single geometric constraint parameter, x plus y divided by 1 minus xy. Applying this unified parameter keeps the calculation strictly within the safe nominal boundaries of the truth table. By processing a single mathematical block, avionic systems bypass cumulative tracking drift, trading hardware processing risk for mathematical certainty. Down at the microscale of physical hardware, rapid alternating current signals forcefully propagate through complex cascade filtering stages. Inside aerospace antenna arrays, the phase angle of cascaded phase shifters is defined by the physical ratio of electrical reactance to resistance. This schematic plots system impedance for stacked filters. When combined, the net phase shift of the circuit is modeled precisely by the arctangent addition identity. If heat or hardware wear causes the tolerances of these components to drift, the product of their parameters might accidentally satisfy the xy equals 1 condition. When that exact mathematical collapse occurs, the physical system impedance plunges to 0, forcing the phase angle to spike vertically into a 90-degree resonance state. That sudden 90-degree resonance acts as an impenetrable physical wall, violently reflecting high-power radio signals streaked back into the delicate transmitter. In RF hardware, a 0 in a denominator directly initiates a destructive resonance loop. In the digital logic tier, flight simulation and guidance software calculate continuous navigation headings. Relying on the standard inverse tangent function to process a y over x ratio introduces a severe spatial hazard. This coordinate map shows the spatial ambiguity. Because dividing two negatives yields the exact same positive ratio as dividing two positives, standard code cannot differentiate between northeast and southwest. If an autopilot relies on this raw calculation, its heading logic will violently flip the moment the aircraft crosses the singularity boundary. Software engineers built the Arctan function specifically to prevent this navigational failure. The Arctan function operates as an algorithmic mirror of the truth table. It explicitly checks the positive and negative signs of the inputs to apply the exact pi phase corrections required. Hard-coding these exact piecewise mathematical constraints into the logic allows the program to process data seamlessly across the boundary line. These programmatic manifestations of pure mathematical limits guarantee a full 360-degree navigation envelope. A single geometric identity acts as the foundational load-bearing pillar for three entirely different engineering disciplines. In radar tracking, processing the unified equation prevents cumulative spatial drift. In RF hardware, actively avoiding the denominator singularity prevents a circuit from reflecting itself to destruction. And in flight guidance, hard-coded piecewise conditions maintain unbroken directional awareness. The master arctangent addition identity governs all three applications. The singularity at x times y equals 1 is an uncompromising physical constraint. Top-tier engineering requires recognizing that equations are the literal blueprints for maintaining system stability in the physical world.